Fields Medal is often considered the most prestigious and highest honor a mathematician can receive. Sometimes it's called the Nobel Prize of Mathematics. In 2014, Dr. Maryam Mirzakhani became the first woman to receive the Fields Medal. Her math accomplishments started at a young age. As a teenager, she was a gold medalist and perfect scorer at the International Math Olympiad. Mirzakhani continued to shine in the field of mathematics until she tragically died in 2017 at the age of 40, too soon to have exhausted her potential. Math Prize for Girls would like to honor her memory and her amazing accomplishments. Advantage Testing Foundation's Math Prize for Girls will formally name the annual Keynote lecture at the award ceremony the Maryam Mirzakhani Keynote Lecture. That tradition starts today, right now. Our 2018 inaugural Maryam Mirzakhani keynote speaker is Dr. Duchin. Dr. Duchin completed her Bachelor of Arts in both mathematics and women's studies at Harvard in 1998. A year later, she earned a master's degree in mathematics at the University of Chicago and continued her work there with a doctorate in mathematics in 2005. Duchin is now a professor at Tufts University and leads a working group on the mathematics of gerrymandering. Her main areas of study are in geometry, the study of shapes, topology, the study of stretchy shapes, and dynamics, the study of how systems evolve through time. For instance, one of her recent math papers is called "You Can Hear the Shape of a Billiard Table." Professor Duchin and her collaborators prove that if you know the sequence of sides struck by a billiard ball, then you can usually work out the exact shape of the table. In the last few years, Professor Duchin has been focused on how to use mathematics to understand redistricting, where the shapes of districts has a huge impact on who gets elected to represent us politically. With a great team of collaborators around the country, she's been organizing conferences and trainings and working to get out tools for community organizations and reform groups. This summer, she helped lead the Voting Rights Data Institute for 52 students from around the world. Please join me in welcoming Dr. Duchin, who will speak to us about random walks in theory and practice.
Hi, it's great to be here. And one of the reasons I was excited to come is that, like many of you, I've been interested in and excited about math from when I was little. But it took a long time to have a picture of what kind of a career might look like as a grown-up mathematician. And so I want to tell you a little bit today about some of the things that I think about and work on, and about this recent turn in what I do from being just pure abstract mathematics to being very applicable. It's also an honor to speak in a forum newly named for Maryam Mirzakhani, who's actually a mathematician I got to know in my field, and some of the work that I'll be talking about is very close to the things that she would think about as well. She was a real inspiration for me and for many. Okay, so theme of the talk is random walks. And so what are random walks? They are processes where you move around in a way that's dictated by some sort of probability. So here's the very simplest one, is a random walk, very simple, non-trivial one, I think. A random walk on the integers. So as it says here, suppose you start out at 0, at the integer 0, and you do a simple random walk where you flip a fair coin, say, and you move either to the left or to the right, depending on what you flip. So here I've got a little animation showing us how you might start. And then you can ask questions like, where do you end up after a long time? And there's nothing special about doing this in one dimension. You can do this in higher dimensions too. So this is a picture of a random walk on the integers in 2 dimensions, the integer lattice in 2 dimensions. So when you study these and you try to understand how the system evolves over a very long time, what kinds of questions might you ask? So here's a picture that shows a pink dot like on the previous ones and maybe part of a path where it moved around the integer lattice at random. Well, there are lots of questions you can ask. For instance, here's a very natural one. What's the probability of return, of exactly returning to the position that you started with? So if you look in this particular picture, you'll see that it starts out somewhere and it kind of wanders away, and it looks like it's gotten a little bit lost. And you can wonder if it continues to proceed at random. Here, there's a 1/4 probability to every move of going north, south, east, or west. How do we feel about the chance that it will eventually come back? Well, if you start to think about this, what you might believe is that on the line in one dimension, there it feels like it's pretty likely, maybe, that you'll eventually come back to where you started. In the two-dimensional case, there's a little more room to get lost, right? Does it sort of feel that way? And of course, you could go up one more dimension than that, or higher if you like. In the three-dimensional random walk, you might move 6 different directions, equally likely, north, south, east, west, up, and down, right? And then walk around for a long time. Well, there's a beautiful theorem, just to give you the tiniest little glimpse into the sorts of things you can actually prove in this subject. There's a beautiful theorem about recurrence, and it has an excellent slogan form. Here's the slogan version of the theorem. A drunken mathematician will eventually find her way home, but a drunken bird flies forever. Okay. So what does this mean? This means that there's a transition in between 2 dimensions and 3. If you do the random walk in the plane, and here you're imagining a drunken mathematician wandering around the streets of a city, with probability 1, eventually that wanderer will recur to the initial point. But that's not true as soon as you get up to 3 or more dimensions. A bird can fly forever. That make sense? Questions? Okay, so this is just the gateway to an enormous field of inquiry where you can study all kinds of counterintuitive things about the asymptotic, the long-term behavior of systems like these. Okay, but that was a line, a plane, and a 3-dimensional space, and there's no reason to stop there. So we don't have to restrict ourselves to, vanilla Euclidean space. We can study lots of other kinds of geometric spaces, and we can wonder about the long-term behavior of random walks. So here's a hyperbolic space. Here's one of my very favorite spaces to study. This is called nil, or the Heisenberg group. And after all, sometimes a space doesn't even look like a space at all. You can consider the space of binary strings, for instance. Okay. So in a topological space, your random walk might move around in position from time to time. In the space of binary strings, you might start with a string of 0s and 1s, pick one at random, and flip the digit to the other kind, right? And so I've shown you a path of that random walk. And all of these have some deep, some surprising, some sort of non-trivial structure to the asymptotics of the random walks. I'll say a little bit more about those as we go. Okay, so I studied something like this in my dissertation, my PhD thesis. So in my thesis, the question was one about the space of surfaces. So what you see here is what's called a surface of genus 1, 2, 3, 4, 5, 6. It's got 6 holes, so it's called surface of genus 6. And it turns out that if you conceive of all the different ways that you can measure distance on a surface like that, that there's a beautiful way to study those all at once. In general, so this turns out to be a 30-dimensional space. Not 1, not 2, not 3, but 30. Okay. So I wanted to understand random walks on this 30-dimensional space of metrics on this surface. And so here was the random walk. So now I have a space and I want to explore it. If I want to do that through random walks, I need to understand what my moves are that I could take at random, right? And so the random moves that I studied here were twists. And the idea was take this surface, take a curve. You see some curves drawn on the surface. And the move is a twist move where you cut the surface open, you twist it all the way around, and you glue it back. It's called a Dane twist on the surface. And so what I studied was what happens if you pick random curves and twist and you do it again and again many millions of times. What could you say about how the geometry of that surface is changing? And here in a nutshell is what I was able to show. The long-term trend, even though that sounds like you might get completely lost, the long-term trend is very organized. And that's maybe a theme when it comes to the study of random walks. So it's, when you do that twisting process, it's just as though you had flattened out the surface and then started to stretch it gradually in one direction while compressing it in the other. And this turns out to be a really excellent, faithful model of the long-term behavior of the twist walk. I hope that's not obvious, because that took me years to prove. Okay, so let's turn to what you could possibly use this for. So I want to tell you about this really fun, really surprisingly deep application to redistricting. So first of all, can I see, just with a show of hands, how many people here would say that they know what redistricting and maybe what the word gerrymandering, what those mean? Can you raise your hand if you know what those mean? And can you raise your hand if you have no idea what those mean? Okay, great. Thank you. So let me tell you a little bit about what those mean, even though it seems broadly familiar. Here's the idea. We're going to get completely out of the realm of 30-dimensional spaces of genus 6 surfaces and start to talk about American politics. In the US, we have a Congress that's made up of a Senate and a House. And we elect representatives to the Senate and the House in quite different ways. So we have 50 states, and each state, no matter whether it's California or Wyoming, each state sends 2 people to the Senate, no matter how big it is. And what happens is that we have an election. Senators have a term of 6 years. And every 6 years, they stand for election, and statewide, whichever candidate gets the most votes is elected to that office. Okay, so that's the Senate. The House is a little bit more complicated. So the House has 435 people in it, and the Constitution tells us that how many each state gets depends on that state's population. So we have a census every 10 years. There's a big one coming up in 2020 that a lot of us are very nervous about. And the census enumerates all the people in the country. And last time, for example, it enumerated Massachusetts' residents, and it found that Massachusetts had just over 2% of the US population. Okay, so how many representatives should Massachusetts get? Well, if it is about 2% of the population, and there are 435 people in the Senate, then its fair share, its proportional share, would be 2% of 435, which is 8 point something and rounds to 9. Make sense? Okay, the actual story of how you round those numbers up and down is kind of a hilarious drama of its own, the subject of the very first presidential veto in US history, and a whole complicated story. But for Massachusetts, it's pretty easy. So we, at the moment, have 9 representatives in the Congress. Okay, here's where redistricting comes in. So after that number is settled on, after Massachusetts is declared to have 9 representatives, then it's the job of the Massachusetts legislature to take the state and cut it into 9 pieces. And the only rule, the only hard and fast rule, is that those pieces should all have the same population. 9 pieces of equal census population, okay? And then what? Then each of those districts holds an election, and whoever gets the most votes goes to DC to represent Massachusetts. Make sense? Okay. So there it is. That's redistricting, and that's what I study because as a mathematician, when I started to first hear about this problem, I thought, there are way too many ways to cut up Massachusetts into 9 pieces. So whoever gets to choose just has a whole lot of control of the process. And that's the story of gerrymandering. When you're in charge of drawing the lines, you get a lot of control about who lives in those districts and a lot of control over who will eventually end up representing you in Congress. So that's the problem to study. And now here's the fact. So at first, when I started thinking about this, I was teaching a class on voting for college students, and I thought, I'll do a little unit on it, and little did I know it would become my full-time obsession. Okay? And that's because it turns out the math is way, way harder than it even sounds. Okay, so I'm going to try to illustrate that for you. Let's start with a toy problem. Forget Massachusetts. Pretend we wanted to redistrict to the 7 by 7 grid of squares. So I just want to cut it into, say, 7 districts of equal size. So 7 districts of 7 squares each, right? For instance, I could take the columns. That would be one way to redistrict the grid. How many ways are there in all? 158 million, right? As it turns out. Okay. So that's a lot of ways to do it, and it's hard to have them all in your mind, but it only gets worse. So for the 9x9 grid, there are 700 trillion ways to do it. And why am I telling you 9x9 when 10x10 is such a round number? It's because I don't know the answer. It's been running on the fastest computers, the fastest public computers at MIT for almost a month without reaching its answer. And so something I want to emphasize about this problem of how many ways to redistrict, it's not just that the numbers are big. I mean, 700 trillion, I don't know how impressed you are with that as a big number. But the actual process of enumerating them has incredible complexity that goes beyond just the size of the numbers. Okay, so this sounds a little bit depressing to me, because if you want to evaluate one way to cut something up, what you should really compare it to is all the other ways. And what I've just told you is that you're out of luck. You're not going to be able to figure out all the ways to cut up Massachusetts or a bigger state like, say, Pennsylvania. Well, the talk is called random walks, and so the good news is we can't count, but we can random walk. So what I've got here is, remember there were, 150 million ways to cut up this grid? This process that you're watching is a random walk on the space of districting plans. Okay? So how does it work? You start with a plan, and then at random, you pick 2 squares and you change their assignments. You change their color, you swap their colors. That's what this particular, there are lots of other ways you could do it. There are lots of other random walks you could choose, but this is a very natural one. Okay, so this is gonna turn out to be an extremely powerful device. When you can't fully list something out, you can at least randomly generate a sample. And if you have some good fortune, the sample that you build that way will be representative of that full universe, even if you can't view the full universe of alternatives. Okay. So at this point, you might wonder, how realistic is this to the actual problem? And, actually, surprisingly realistic. So this is a picture of Iowa, and these are Iowa's 99 counties. And Iowa actually has a rule that its districts must be built out of entire counties. So that means the problem of finding all the possible districts in Iowa really is just a random walk on that graph of those 99 counties. Okay, so this is really a process that we can use to get our hands on a giant batch of possible districting plans. Okay, so let's move to an actual state. Here's the lovely state of Pennsylvania. And Pennsylvania, being about twice as big as Massachusetts, gets 18 districts in the last census cycle. What you're looking at here is 4 different possible ways to cut Pennsylvania into 18 pieces with the same population. And I show it to you this way because this is sort of often how you encounter these maps, is just as pictures. And maybe if you're from Pennsylvania, who's from Pennsylvania? No Pennsylvanians in the house. Shocking. Maybe if you're from Pennsylvania, you recognize what's going on in some parts of the state. You see those little districts where Philadelphia and Pittsburgh are, because the population's denser there. Big districts in the more rural parts of the state. It's still, I would argue, very hard to tell with your eyeballs what the map is actually doing and what quality of representation it would be likely to produce. What you're looking at here is 2 different maps made by Republican legislators, one map made or commissioned by the Democratic governor, and one made by an independent outsider. Do these look very different to you in terms of, if I showed those to you, well, I am showing them to you, and I asked you which ones are gerrymandered and which ones are fair? Anybody have a feeling about that? One on the left, what about it? Look bad? Yeah, right, exactly. I mean, when I look at these, all I see is that the one on the top left looks a little suspicious. right? And what's the one on the top left doing that might make you feel that way? It's got these distended, eccentric shapes. I like to call those kinds of shapes tumors and fractals, right? They don't look plump, they don't look squat, they don't look symmetrical, and they make you feel like maybe something's been going on. Well, indeed, that map was thrown out by Pennsylvania's Supreme Court as a big partisan gerrymander. But the Republican legislature came back with a second map. And as I said, the others come from a Democratic governor and an independent outsider. And for the other three, I don't think you could tell them apart anymore, right? I don't think those shapes will offend your eye or sear your retinas anymore, right? And so you need other techniques to decide on what these maps are doing. And what I want to propose, what's become maybe a breakthrough in the study of redistricting, is that we can use random walks to really get a handle on how the maps behave. And with the time I have left, what I want to introduce to you is the idea that if you can see, if you can explore enough of the universe of possibilities, then you can start to see whether a map behaves outside of the reasonable range. Okay, that's where we're going with this. That's the first legislature map. That's the alternative legislature map. This is the governor's plan, and this is the outside plan. Okay, so as I've been trying to tell you, the possibility space is way too large. Okay, how large is it? It's no longer in the millions, trillions, quintillions. It's so big that it's literally true that if you were to enumerate the plans at 1 microsecond per plan, it would take until the heat death of the universe to get them all. Okay. So we're simply not doing it. So it's random walks or nothing. Okay, this slide, this is probably the hardest math slide I have in the talk. So let me take a little time to try to explain it. This is what this random approach, this is what mathematicians can bring to the table here. We get to come up with some models to try to explain why a random sample might do a really good job of exploring the space, even though it's nowhere near finding every possibility. The reason is an idea called mixing time. So, which is very close to what I was studying in this dissertation of mine way back in abstract math land, back at the University of Chicago. Okay, so what happens is, even long before you see even a fraction of the possibilities, you achieve something called mixing when the sample that you've accumulated has almost the same properties as the whole space at large. So for any function that you might want to measure, its values on the sample will give you some sort of bell curve that matches the distribution in the whole universe. And that feels a little bit like magic. Okay, so on this slide, I want to try to tell you that that can happen pretty fast. So first, remember my first simplest random walk where you just walked left or right on a path. And then I had this other random walk where you just walked north, south, east, or west around a grid. And then I had this other random walk where you walked through binary strings. Look how fast they are. If capital N is the number of objects in the space that you're studying, it only takes you time n squared to mix on the path, time n to mix on the grid, and time log n, log n, which is very fast, to mix on the space of binary strings. So depending on the geometry of the landscape that you're searching, you can get very efficient samples very quickly. And that's what we're counting on to make this redistricting analysis work. Okay, so to sort of bring this to a punchline, let's just do it. And I want to give you some indication of how well this works in practice. So let's take a look at this fictional country. This is now a 10 by 10 grid. And let's suppose that these are its voters. So the 10 by 10 grid has 100 units in it. And I want to imagine that 40% of them are orange and 60% of them are pink. Okay. So I'm going to cut this grid into 10 districts. And so probably we have an intuition, a shared intuition, that if the plan is fair, since orange has 40% of the votes, it should get 40% of the seats. Does that seem right to everyone? Does anyone think that it would be more fair if orange did better? than 40% of the seats? Does anyone think it would be more fair if orange did worse? Okay, let's see what actually happens. So first, let me illustrate that the lines really matter. If I know where the people are and I can draw the lines on top of that, I have a lot of control. So here's plan A. It's got 10 districts that you see in the picture, and 2 of them are safe orange seats and 1 of them is competitive. Everybody following this? Okay. Here's plan B, which all I did was rotate those rectangles, but now it's got no safe orange seats and 3 that are competitive. Here's plan C, which did what I think most of you decided was the fairest thing. It gave 40% of the representation to orange. Okay? And here is an orange favoring gerrymander. So here I sat down by hand with that distribution, and I tried to find a way to get orange as many seats as mathematically possible. The most safe seats orange could possibly get is 6. Exercise, prove it. Here, I found it. It took me a little over an hour. That's actually true. And when I take this exercise sometimes and I give it to students at schools, they can find it in 15 minutes, but it took me an hour. Okay, so that means that orange can get anywhere from no seats to 6 seats out of 10. From no representation to 60% of the representation just from drawing the lines in different places. Okay, so that's an illustration of the power of the districting pen, right? So I got a computer. Took about 30 minutes to write some code to do these random flips, and did runs of 100,000 random alterations. Okay, so it just bloop, 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 jumps around in the space of plans. It finds 100,000 different alternatives. And remember, the total size of the universe is in the quintillions for 10 by 10, we think, once the computers get there, right? 100,000 is just not very big. It's actually a very small sample in a very big space. So how did we do? Well, first thing I want to tell you is, what does it take to make 100,000 plans? So what you're looking at here is a giant supercomputer that lives at the University of Illinois, and that's actually used for redistricting problems. And you might think I have to run this on that, but no, it actually takes 15 seconds on even this terrible laptop that you're looking at here is enough to get these batches of 100,000 plans. Okay, so it's a very computationally efficient process. But how does it do? Okay, so let me show you actually what happened. So here are 2 different plans, plan B and D from my list before. And remember, B was not that favorable to orange, only 1.5 orange seats, right? 0.5 was a competitive one. D was my gerrymander with 6 orange seats. So those are sort of starting from different extremes. Look what happens if I do a random run. So this histogram shows you how many seats the orange side got over my 100,000 histogram. Right, so the way to read this is that the most common thing was 2.5 seats for orange. And that happened about 6,000 some times. Everybody with me, understanding how to read this? Okay. Let's do another run. There it is. Let's do a third run. There it is. They're not exactly the same as each other because there's randomness involved. But broadly, those histograms are, I would say, in the same place. Do you guys agree? And actually, if you take the mean number of seats for orange over those histograms, you get something that's about 2.3, no matter which of those runs that you do. Okay, so that was starting with 1.5, and what you could see is 1.5 was kind of too low. Orange tended to get better representation than that. All right, so what do we think is going to happen if I start with 6 orange seats? Well, I'm still going to get a bell-shaped histogram, but you might think it's going to move all the way over to where the 6 is, right? Right, but it doesn't. Check it out. 1 run, 2 runs, 3 runs. The histogram that I get is in almost exactly the same place. That's really good heuristic, informal evidence that I might be sampling representatively. It's not overly dependent on where I start the walk. And by the way, I can tell, I'm not going to show you all this on slides, but if I were to sample 200,000 or 1 million, the histogram would be in the same place and with the same shape. So 100,000 seems to be enough to actually sample representatively from this space. All right, so there's a few things to notice here, and one of them was, remember how we thought that the most fair outcome might be 4 seats for orange? Take a look at 4 in these histograms. It's all the way down kind of towards an edge of the histogram. And that's actually pretty interesting, and I think pretty surprising. Something about where the orange people live in that state makes it very hard for them to get proportional representation. Okay, so if I neutrally choose a plan, if I'm not focused on the representation for orange, they're very likely to be underrepresented, not because they didn't turn out to vote, not because they didn't field the right candidates, but because there are structural, geometric features preventing them from getting what we might think of as their fair representation. Does that make sense? Okay, so with this kind of analysis, you can study not just toy problems like this, but an actual state. So there's a reason that I had all those maps of Pennsylvania up. So I was recently hired by the governor of Pennsylvania. Believe me, that phone call surprised me as much as you. So I was recently hired by the governor of Pennsylvania to help them redistrict the state. And that's because after that plan that I showed you before, the tumor fractally plan got thrown out, there was about a month that everybody had to redistrict Pennsylvania and it was going to hold up for years and have big consequences for their representation. And so the governor, Tom Wolf, who I believe is the only governor in the country with a political science PhD, he said, we should probably get some experts in to study this. So this, for me, was a really great opportunity, and let me tell you how it turned out. Those maps that I showed you of Pennsylvania several slides back, actually, let me put them back up. Those 3 might look the same, but they perform incredibly differently. The legislature's new proposed plan had so much advantage for Republicans packed into it that it wasn't even in the small part of the bell curve, it was in the invisible part of the bell curve. Whereas the governor's plan, which even though he hired me, I had nothing to do with making, I was just asked to analyze plans. The governor's plan hit the meaty part of the curve, and so did the independent outsiders plan. And so what's the outcome of this? It turns out to be a pretty big deal. The Pennsylvania Supreme Court, without waiting for the US Supreme Court, enacted this remedial plan that you see on the bottom. The primaries in May were conducted under it, and Pennsylvania will be getting a very different kind of representation. And a small note about that I think is worth saying at Math Prize for Girls. Before this process, Pennsylvania's 18 seats were held by 18 men. It was the largest congressional delegation in the country to be all male. New map comes along, shakes up incumbency, and 7 women won their primaries in May. Yeah. So we have to see what November will bring, but for me it was an honor to be part of a process that could have such a deep impact on the way that Pennsylvania's representation looks. Okay, so if I can scoot back, I have to, I guess, let my animations play again. So if I can scoot back ahead to the end of the story here, it's that this approach really does seem to do a good job of telling apart just structural advantage for one side from excessive advantage produced by line drawing. The whole country is incredibly complicated. The landscape of ways to redistrict it is so big, we literally don't know how to think about it. But as civic-minded mathematicians, it's our job to explore. Thank you. I don't think we probably have time for questions, right?
Maybe 1 or 2.
Okay, 1 or 2, but I'll just mention our organization has a new website that debuts tomorrow. And on that website are a lot of interactives where you can explore the math that I've been talking about. So if you wait 1 day and visit our website, I invite you to get a look at how the mathematics of redistricting really looks. So if there are 1 or 2 questions, it would be my pleasure, and I'll know that you weren't just surfing your phones the whole time. So that would make me happy. And otherwise, I hope to hear from you in the future. So questions, 1 or 2? Yes? Okay, so the question was, what are the future plans, what to work on next? So before this summer, there was a lot of attention on the US Supreme Court and a lot of hope that the court might smile on an approach like this. And then we had some news this summer, retirement, shook things up on the Supreme Court. And the short answer is people aren't really waiting on the court anymore. And what I think is exciting is that people are turning to the states with the success of, Pennsylvania is actually the only state so far that's had success in redoing its maps. But many states are now looking at reform measures, at citizens' initiatives, getting things on the ballot. And so one thing our group is doing is consulting with community organizations and reform groups around the country, such as in Oregon and Virginia, and trying to help them think through what new rules to write in as we wait for the next census and the redistricting to follow. Is there one more question before we call it a day, before I call it a day? Okay, thanks for your attention.